Hello there. In this lesson, we're going to learn about how we can use the equilibrium constant to be able to tell which way a chemical reaction, a reversible chemical reaction, will move in order to get to equilibrium. We're going to use a little teeter-totter or seesaw, whatever you want to call it, as an analogy to help us to make that determination. And we'll be introducing a new symbol, Q. Okay, so again, the direction of an equilibrium reaction depends on what you start with. When you get to equilibrium, both the forward and reverse reactions will be equal, but in opposite directions. But when you start off, you won't necessarily be at those equilibrium conditions. And so if there's a greater concentration causing a reaction to go in one way over another, then there will be a shift in order to get to that equilibrium condition. And so you have to compare what you start with to the equilibrium condition and know which way that will be. So right off the bat, you need to be able to look at the equilibrium constant and be able to sort of make a judgment about what it's going to be like at equilibrium, like in general. So first of all, we're going to look at when we have pretty big values for K. When you have a pretty large value for K, remember K, the equilibrium constant is always the right side over the left side. And so if the K value is really big, that means there's going to be lots and lots on the right and very little on the left. And then the inverse of that, of course, is when you have a very small K. We're going to use this 10 to the 3 or 10 to the negative 3 as sort of a cutoff. But usually there's lots of equilibrium constants that are pretty much higher than that or lower than that, that you'll be able to tell right away that there's going to be like a lot on one side and almost nothing on the other side, like very, very small concentrations. And so we use that later on to be able to predict the direction a reaction will go. The in-between section, that's the part that we're going to need a little bit more help with to compare your starting conditions to where you're going to end up with at equilibrium. But right off the bat, you should be able to tell something just by looking at the order of magnitude of the equilibrium constant value. Okay, so right off the bat, if we look at these constants, we can tell that at equilibrium that there's going to be a lot of C. And A and B are going to get mostly used up, or if one of them's limiting reagent, at least the limiting one will get pretty much used up. And so this will be like big amount, and something over here will be small, at least one of them. And we got a little guy like this, that means there's going to be lots over here. So this will be the big side here, and this will be very small. And then we have this quantity here where it's sort of in between. And for these intermediate type values of the equilibrium constant, then you're going to have similar quantities on either side. So once you know the equilibrium constant, we can use that to be able to solve for unknown quantities at equilibrium. In this case, we're given an equilibrium constant of 12, and we have a situation where we're starting off with everything on the left-hand side of the equation and nothing on the right-hand side. So we don't have to make much of a call here. We know that the only way this reaction can go to get to equilibrium is to the right, because that's the only way it can go. So then you can fill it in just like you would any other equilibrium change on your ice table. You know you're going to lose from the left-hand side and you're going to gain from the right-hand side. This is a nice simple reaction where 1A turns into 1B. And that means at equilibrium, you're going to have 0.85 minus x, and over here, you're just going to have x. And so you can solve for the equilibrium quantities or concentrations using the constant. So we know that this constant is going to be the concentration of B because it's on the right over the concentration of A because it's on the left. And so at equilibrium, B is going to be x, and A is going to be 0.850 minus x. And the constant is 12. So then we'll move things around here. So it's going to be 12 times 0.850 minus x. It's going to equal x. Let's use my calculator here. 12 times 0.85 is 10.2. How about that? So we got 10.2 minus 12x equals x. And so move them all over to the other side. So there's 13 x's, and this is 10.2. And we'll divide both sides by 13. And we'll end up with x. So 10.2 divided by 13 is 0.78 moles per liter. Oh, I guess. Yeah, so, 784, my bad. That's a 4 in there. Okay, so then you can solve for the equilibrium concentrations once you have the value of x for the change. So the 0.850 minus 0.784 is, so we're going to end up with 0.66 moles per liter for A, and the 0.784 over here moles per liter for B. So once you know the direction you're going, you can always work out the concentrations using a little algebra to solve for the equilibrium conditions. So oftentimes you can compare your initial concentrations to your K value and come up with a pretty quick educated guess of which way the reaction is going to go just by looking at the values you have. So with really like big or small values, it's usually pretty easy to figure out. So this has a huge value for the constant, which means, and if you look at the initial concentrations, we only have stuff on the left-hand side and there's nothing on the right. So the only way this reaction can go is to the right, right? That's the only place it can go. And because this K value is so large, it's going to end up being that at equilibrium, there's a lot more B than there is A. So this is going to go to the right a lot. And then if we look at this next one here, you can see we have sort of similar quantities for A and B, but still a pretty big value for K. And so this one's going to the right a lot as well. Not quite as much as the first one, but still a long ways. This one here is a very small value of K. We are starting off with lots on the right and a little bit on the left. So that means that this reaction is going to be going this way, because at equilibrium you're going to have a lot on the left. And so again, this is going a lot. Here's one with a really tiny value of K, but only stuff on the left-hand side. So this one also has to go to the right, because that's the only way it can go. But it's very close to its equilibrium quantities. Because of this value being very small, that means most of the stuff's going to be on the left and only a little on the right. So this is only going to move to the right a little, right? Only a little bit to get to its equilibrium concentrations. So you can see the big and the small values for K can help you to determine the direction of a reaction pretty quickly, but not every reaction is going to be that way. And another tool that we can use to determine direction is this reaction quotient, given the symbol Q. Now Q is worked out the exact same way that you would work out the equilibrium constant. So with a constant, you take the equilibrium concentrations. In this case, the right side is 0.785 moles per liter, and the left side is 0.065 moles per liter. And if you divide those, you get a nice 12, right? It's from the previous question. But the quotient, the reaction quotient, does the same exact thing, but it uses the initial concentration. So the Q for this would be 0 moles per liter all over the 0.850 moles per liter. And what you can do is, answer that's of course going to be 0. What you can do is, this is where the little teeter-totter comes in. If you imagine a little teeter-totter with a Q on the left and K on the right, you can just use these values of Q and K to be able to tell you which way they're going. If you just sit them onto the teeter-totter, the bigger one is the side to which it's going to lean. So here's your three possibilities. Let's say the Q value is larger. That means the teeter-totter is going to shift this way and the reaction is going to go to the left, right? And then if Q is the same as K, that means you're already at equilibrium. So the reaction won't shift one way or the other, and it will be at balance or at equilibrium from the get-go. And then if the K is larger, then that means then the teeter-totter shifts to the right, and that means the reaction is going to go right until it gets to the equilibrium conditions where the rates of reaction in both directions will be the same again. So there's another way that you can determine the direction. So let's have a look at another situation, same equilibrium, same constant, only this time we're given quantities to start with here. We got 0.025 on the left and 0.55 on the right. So this is a good candidate for using Q because we can't really tell. We know that the right side is going to be bigger because 12 is greater than 1, but we don't know if that's big enough. So we can take this right-hand side, 0.550 moles per liter, divided by 0.025 moles per liter. And if you punch that into your calculator, let's see here, 0.55 divided by 0.025 equals 22. 22. So if we put that on the little teeter-totter here, we got 12 on this side, we got 22 on this side. That means this reaction is going that way. So going this way, so that means this is going to be a plus x on this side, a minus x on this side, and we should be able to work out our equilibrium concentrations once we have that information. Again, you just sub in the equilibrium constant, 0.550 minus x on the top, 0.025 plus x on the bottom. And then you're going to spread that out, so 12 times 0.025 plus x equals 0.550 minus x. And let's see here, what's 0.025 times 12 is 0.3. And then plus 12x equals this. Minus x. So let's group all those things. Maybe let's make the 13x on the left-hand side here. We've got 0.550 minus the 0.300. So that means 0.250. 13x. X will equal 0.25 divided by 13. And we end up with 0.019. So we can sub that back in there. I'll use a different color. So 0.025, 0.025 plus the 0.019 equals, what would that be? 44, 0.044 moles per liter for this guy. And then subtract the 0.019 from that, so 0.55 times 0.019 is 0.531 moles per liter for that guy. So there we go. We have the equilibrium quantities using the direction that we determined from the quotient. Alrighty, one last thing before we go. Even if you get your reaction quotient and direction wrong, if you follow through with your algebra correctly, it should still give you the correct answer. And so some people ask me, like, why even bother with the reaction quotient? And that's a fair point, because if you're good with your algebra, you could almost just pick a random direction and it would solve it for you that way. Anyways, just to show you that that's the case, if we thought the direction was going this way instead, that would be a minus x here and a plus x here, and 0.025 minus x, and this would be 0.550 plus x. Then we slap it into that same equilibrium expression, 0.550 plus x, and the 0.025 minus x, and you work it all out again, so 12 times the 0.025 minus x equals the 0.550 plus x. And if you sort everything out, it ends up being the same, 0.3 minus 12x equals 0.55 plus x, and then we'll move everything up here, and it'll be 13x again on that side. Only this side it's going to be negative 0.250, and then x ends up being negative 0.019 moles per liter. So it's the same exact value, only it's a negative sign. So that would change the signs of these guys that remain, and you'd end up with the same equilibrium quantities. So there you go, a little solace that even if you're not quite sure which direction it's going, if you follow your algebra, it will tell you. All right, take care. Talk to you soon.